Imagine dropping a file named libselenox.so.8 into an enterprise Linux server. You run it through VirusTotal, and it comes back completely clean, 0 out of 66 detections. That file remained undetected in production environments for 13 months, spanning from July 2024 to August 2025. Every major antivirus engine on the market flagged the file as non-malicious. Yet, that same file was actively providing attackers with persistent, root-level SSH access to the compromised machines. This is the work of two specific malware variants, Plague and a commercial implant sold on Russian cybercrime forums called PamDora. Deploying these tools bypasses the need for burning 0 days or brute-forcing firewalls. Instead, they subvert the server's logic from the inside out. They achieve this by deploying malicious Pluggable Authentication Modules, or PAMs. These modules grant complete authentication bypass and silently harvest credentials from every legitimate user who logs in. Today, we are going to deconstruct how these implants integrate into the Linux architecture and how to hunt them using behavioral analysis. The network perimeter remains intact, but the internal locks have been replaced, rendering traditional security assumptions obsolete. To understand the subversion, we first have to look at the execution flow of a legitimate Linux authentication request. PAM decouples privilege-granting applications from the actual mechanism of verifying a user's identity. As shown in this diagram, when an incoming SSH request hits the server, it first connects to the SSHD process. SSHD does not check the password itself. It hands the request to the central libpam library. libpam then consults the configuration files inside the etc/pam.d directory to determine the routing logic for that specific service. The final step is the execution of shared objects, like pamunix.so, located in the /lib/security directory. These interact with the shadow file to verify the user. Because the operating system implicitly trusts these shared objects, any entity that controls the .so files controls the system's concept of truth. Consider an attacker who has obtained root access and is establishing persistence. They drop a malicious shared object into the /lib/x8664linux.gnu/security directory. These implants specifically target the pam/sm/authenticate function, inserting a malicious node directly into the authentication pipeline. The Plague backdoor performs this entire hijack in fewer than 100 lines of code. The first capability is Authentication Bypass. The module is programmed to recognize a hard-coded static password. When the module receives this password, it unconditionally returns a PAM success flag to SSHD, skipping the legitimate verification process entirely. The second capability is Credential Harvesting. The module silently intercepts legitimate users as they enter their actual passwords. It immediately applies XOR obfuscation to the stolen data. These encrypted credentials are then stored in randomized /tmp files for later exfiltration. By hooking the core API, the backdoor operates within the expected execution flow, making it indistinguishable from a legitimate login process. This raises the central question: why does a fully updated EDR or antivirus agent miss this activity? It exploits an architectural blind spot. PAM modules load directly into privileged memory spaces as legitimate shared objects. Because they do not spawn suspicious child processes, they rarely trigger behavioral heuristics. Plague relies on multi-layered string obfuscation to defeat static analysis. The outermost layer uses simple XOR encryption. The second layer employs custom pseudo-random routines designed to hide memory offsets. The final layer uses a deterministic random bit generator to scramble the underlying sensitive strings. The malware also includes anti-debugging mechanics, checking for l.so.preload manipulation and verifying its own file name to dodge sandboxes. For forensic cleanup, the module unsets the SSH correction and SSH client variables. It then redirects the attacker's shell history to dev null. The malware survives because it turns the system's own privileged architecture against itself, leaving no static signatures for traditional tools to find. Because static antivirus relies on signatures that do not exist here, defense requires a focus on behavioral and integrity-based monitoring. File integrity monitoring is the absolute frontline countermeasure. You must establish and verify baseline hashes for every shared object on the system. Pay specific attention to /lib/security and the configuration files in /etc/pam.d. Any unauthorized modification in these directories indicates a critical compromise. Threat hunters should use custom YARA rules to scan small LF binaries for specific function patterns. Specifically, hunt for strings like decrypt phrase and init phrases. Defense is no longer about matching known bad signatures. It is about aggressively enforcing the known good state of the authentication architecture. Securing the stack requires broader architectural mandates for Linux hardening. First, you must strictly enforce multi-factor authentication for all SSH access. MFA neutralizes the threat of credential harvesting because a stolen password alone is no longer enough to gain access. Second, export all authentication logs to an external system immediately. These logs must be shipped to an immutable off-site CM where attackers cannot reach them to alter the record. The authentication stack is the modern perimeter. Assuming a server is secure because the network firewall holds is a fatal error in modern Linux administration.